It's 2:51 and 28 seconds on the 25th of June. We're going to make a Mobius strip with 3 flips. It's going to be a counterclockwise version. I've made it with my Mobius paper. You can see the Mobius paper has been photocopied double-sided. Counterclockwise will be 1, 2, 3. Then we're going to cut it down the middle. As you know, it has one surface, one edge. Surface is what you call a boundary. When you cut it down the middle, Mobius strips with 3 flips end up with 8 twists. To flatten the twists, you need 6 lines to kill all the twists. A line is nothing more than the intersection of 2 planes. All the solutions have now we have the white surface and the black surface. You have this trefoil knot right here. There's one little kink which you've got to get out of it. And now we're going to flatten it. These intersections. We just lay it down and we look for the solution. And that will be right. We'll start right here actually. There's one line. We put a loop right here because it just wants to have a loop right here. We just work quick. It doesn't matter what you do with the solution. They just kind of sort themselves out. Well, we got to put a loop right here because that's where it's been confined to. There's always 2 loops, if not 3 loops. And flattening this separates the surface, the edges. You can see the black edges on the bottom, the white edges will be on top. And the last thing we got to do is this little bit right here, and it's done. So we'll add a half snip here, half snip here. You could take your time and do this so that you get nice symmetries between the vertices, just so they all look very familiar, but usually I just work very quick. Here's our solution. I've seen this one before. I have it in my notebook. What we'll do next is we'll do a knot diagram. So we'll just trace it. So the knot notation will be an overhand knot here. It comes down, it goes under here, it goes up this way, it goes over, under. Oh, my pencils run out. I should use a marker. So we'll do the knot diagram. Goes under, goes over, here it goes over and up, here it goes under, here it goes under, comes around, it goes over here, goes over, goes under, it comes around. So we reduced it to a graph. This is a multi-graph. It has multi-edges and it has loops. There's always 1, 2, 3, 4, 5, 6 vertices, and there's always 12 crossings. So I usually start in this overhand knot and I work this way. It has to go from the over position in one of the loops around into the overhand knot. Actually, sorry, I always start here and I go past the second knot into the overhand knot. So my knot notation will start right here. I don't have a red pen. So it'll be over, under, under, over, over, under, over, under, under, over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And from there we can turn this into a graph. So we'll do the vertices. It'll be 1, 2, 3, 4, 5, 6. This one will be a loop. This one will be a loop. There's an edge, a multi-edge. There's another edge, another edge, another edge, another edge, another edge. Then we have to connect to this loop, and this loop goes down to this loop. And you can see there'll be 1, 2, 3, 4, 5, 6. There's 12 edges. We can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If we want to work out the Betti number of this, it's really simple. How many edges can we take away so there's no enclosures? So we'll take away the loops. 1, 2, 3, 4, 5, 6, 7, and it's 7. So we can see the vertices will be left connected. So we'll draw the vertices now. It'll be this vertice to 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 this vertice. 1, 2, 3, 4, 5, 6. So they all have 12 edges. They all have 6 vertices. They all have a Betti number of 7. And remember, there's 8 twists. There's 8 twists. And it's interesting that the Betti number is always the faces minus 1. And count the faces. 1, 2, 3, 4, 5, 6, 7, 8 faces. So it will be 8 minus 1 equals 7. There's also 8 twists. We were working at the Euler characteristics of these graphs. Most of them are planar, some are not planar. Most of the Euler characteristics equals 0. And I don't know how many graphs there are of all the solutions. That I'm still working on. So that's what we've done. We've turned Mobius strips into flattened kind of fence posts, such as here, into a knot diagram with knot notation, and finally into a graph. It's a digraph, directional. And it actually has a Eulerian circuit because we can start at this vertice, we can travel across all the edges once to get back where we started. So the equation to look up how many Eulerian circuits there are in graph theory, I think it's the best theorem, but that involves doing a matrix, graph matrix and multiplying matrices and finding out the cofactors, which is going to take a bit of time for me to figure out. That's it for my YouTube video. I hope you enjoyed this video on Mobius strip topology. We've been looking at topology and we've been looking at graph theory.